This video is about the magnetic effect of electric current. The specification covers understanding how electric currents produce magnetic fields, describing the construction of electromagnets, and sketching magnetic field patterns for straight wires, coils, and solenoids. In 1820, Hans Ørsted observed that an electric current in a wire caused a compass needle to deflect, demonstrating the principle of electromagnetism. For a straight wire, the magnetic field consists of concentric circles centered on the wire. The field is strongest nearest the wire, and its strength increases with the electric current. The right-hand grip rule helps determine the field direction. Grip the wire with your right hand. Your thumb points in the direction of the electric current, and your fingers show the direction of the circular magnetic field. Use the right-hand grip rule to complete the diagrams below by adding field arrows or current direction. For a flat circular coil, the magnetic field pattern is circular near the wire. The field lines become straighter and parallel through the center of the coil, resembling a bar magnet's field. A solenoid is a coil of wire carrying an electric current. Its magnetic field pattern is similar to that of a bar magnet. The field strength increases with the electric current and the number of turns in the coil. The right-hand grip rule can also determine the poles of a solenoid. Curl your fingers in the direction of the current flow. Your thumb points towards the north pole end of the coil. Apply the right-hand grip rule for poles to locate north or south, and add current direction or coils to complete the diagrams below. An electromagnet is constructed by wrapping a current-carrying coil around an iron core. This combination produces a strong magnetic field when current flows. A major use of electromagnets is in scrapyard cranes. The iron core is a soft magnetic material, which magnetizes strongly when current flows, picking up scrap, and demagnetizes when the current is turned off, releasing the scrap. In an electric bell, closing the push switch activates the electromagnet, pulling the soft iron armature and causing the hammer to hit the gong. This action opens the contact switch, cutting the current. Test your knowledge by labeling the components of the electric bell diagram below. A relay switch uses a low-voltage circuit to remotely switch a high-voltage circuit. Closing switch A magnetizes the electromagnet, attracting the iron armature, and closing the springy contact switch B in the high-voltage circuit. A circuit breaker functions using an electromagnet. Current flows between terminals A and B through a contact and the electromagnet. If the current increases significantly, the electromagnet strengthens, pulling the soft iron armature toward it. Spring 1 immediately pulls the contact apart, disconnecting the circuit and stopping current flow. The circuit can be reconnected by pushing the reset button. Let's review the key concepts covered by filling in the blanks with the provided words. A wire carrying an electric current produces a magnetic field. This field increases in strength if the current is increased. A solenoid is a coil of wire carrying an electric current. Electric charges are deflected by magnetic fields, provided they are not traveling parallel to the field lines. Positive and negative charges are deflected in opposite direction. The motor effect is when a current-carrying conductor in a magnetic field experiences a force, provided the conductor is not parallel to the field lines. The force on the conductor increases if the magnetic field strength or the current is increased. Reversing either the current or the magnetic field direction reverses the force's direction. Fleming's left-hand motor rule helps determine the direction of the force, magnetic field, and current. Remember, the magnetic field is from north to south, and current is from positive to negative. Now, let's apply Fleming's left-hand rule to these four scenarios to insert the missing information, such as force or current direction, or the magnetic poles. A simple model electric motor demonstrates the motor effect using a current-carrying coil placed in a magnetic field, causing it to rotate. The loudspeaker uses the motor effect. An alternating current makes the coil vibrate, which causes the diaphragm to move, producing sound waves. Fill in the gaps to summarize the motor effect. The motor effect occurs when a current-carrying wire is placed in a magnetic field. In an electric motor, the current in the coil produces a torque. The split-ring commutator reverses the current direction every half revolution to ensure continuous rotation. The diagrams illustrate the rotation of the electric motor coil. The split-ring commutator ensures the force always produces a clockwise turning effect, allowing for continuous rotation. Let's revisit the summary question on the motor effect. Use the word selection provided to complete the sentences. Here are the solutions for the fill-in-the-gaps summary. Please review the answers against your responses to ensure understanding.